Good afternoon or morning, whatever it may be. Right now it's close enough to either one. Anyway, welcome back to some atmosphere stuff. Today we're going to make it about a 18-minute discussion on the components of the atmosphere. We left off previously on the ozone layer and how that was an umbrella that set the stage for the development of cyanobacteria, the first organism to appear in the fossil history. And we're going to look at how the advent, or the growth and proliferation of that bacterium changed the atmosphere gradually, yet significantly enough to set the stage for the biodiversity that we see today. And all of the biodiversity, meaning all of the different types of living organisms that interact with the environment as well as one another, are here today simply because of the conditions that the Earth provides. And as those conditions change, organisms that are most fit to survive in those conditions continue to survive and proliferate, and those that were less fit to survive in the changing environment, the less successful they will be, and eventually will, disappear, go extinct. So change brings about change. So it's important to know what the atmosphere is made of. We know a little bit about where it was, where it came from, what some of those ancient components were, right? Remember, primarily methane and ammonia, and a little bit of carbon dioxide, very little free oxygen. And as time went on and sunlight continued to add energy to the atmospheric system, larger molecules would break apart into their smaller components, the atoms that make those molecules up. And with lightning, as well as sunlight, you will get the rebonding of smaller molecules made up of less atoms per unit. So, things continually change. I believe we left off on slide number 4 with new developments, cyanobacteria, and the development of simple plant species. So I'd like to advance to the next slide, which is, I believe, today's atmosphere. I think that's what it's labeled. Yes, today's atmosphere. Okay, so we know the atmosphere is a mixture of many different gases. Some are good for us, some are not so good for us. But we as a species, humans, have evolved over time to be most fit for the specific ratio of components that we experience, for the most part, today. Okay, so some of you may be surprised as you look at the composition of today's atmosphere that oxygen, we're all familiar, we breathe it in and breathe it out. Oxygen is not the primary component. It's actually nitrogen gas. If you are sitting anywhere on Earth, and I'm assuming all of you who are watching are, you are surrounded almost 8/10 of your surroundings atmospherically is nitrogen. You're being bathed in nitrogen gas. And nitrogen gas is non-toxic, but it is not something that our system uses. We can't even absorb nitrogen directly as nitrogen gas. We breathe it in, and we breathe it out. And there's no exchange. It doesn't cross any of our cell membranes in our lungs. It just comes in and goes out. It's just taking up space. Oxygen is merely 2/10 or 21% of the lower level of atmosphere that we're all living in. So your major three components, and they're significantly different in their amounts or their ratios. 78% of all of the atmosphere that we're exposed to here on the lower levels is nitrogen gas, N2. Two atoms of nitrogen bonded together to make a gaseous molecule of nitrogen. 78%. Man, that's a lot. Followed by, in second place, oxygen. 21% of our atmosphere is oxygen. And that has been freed up. O2, two atoms of oxygen atomic, makes one molecule, O2, oxygen gas. So the ratio of the nitrogen to oxygen, 78% nitrogen and 21% oxygen, add that together, 78 plus 21, that gives you 99%. That's almost the entirety of all of the atmospheric gases are represented by nitrogen and oxygen. Doesn't leave a whole lot of room for all of the other gases that we interact with. All right, so 78% nitrogen, 21% oxygen gives us 99% of our atmosphere. The third place holder, the bronze medal, goes to carbon dioxide. And carbon dioxide makes up just short of 1% of the atmosphere. And, some of you may be familiar, have maybe learned previously that we breathe in oxygen and breathe out carbon dioxide. Right? That's true-ish, but not quite as straightforward as that makes it sound. We breathe in atmosphere, and we breathe out, we exhale, basically that same atmosphere minus the tiny little percentage of usable oxygen that our lungs can absorb per respiratory cycle. We're not magically changing what we breathe into what we breathe out as being something completely different. Essentially, what we breathe out is almost exactly the same as what we breathe in. Think about CPR, mouth-to-mouth resuscitation. Someone has lost consciousness and they perhaps have a low level of oxygen in their system. A life-saving technique is CPR. You have to breathe for that person, continually blowing air into their lungs so that they can have a livable supply of oxygen. Now, if it were true that we breathed in oxygen and breathed out carbon dioxide, CPR wouldn't work, right? You'd be breathing into this victim poisonous or useless carbon dioxide, which simply isn't the case. We're breathing out almost the exact same thing as we're breathing in. So keep that in mind, as systems are a little more complex than you may have previously learned. Okay, so carbon dioxide is a very important gas in terms of keeping us alive, in that it is the primary component of photosynthesis, a complex chemical reaction carried out by plants. Plants respire, breathe, so to speak, by absorbing carbon dioxide from the atmosphere, keeping the carbon, linking that to some other atoms we'll talk about briefly, to make sugar, and they release gaseous oxygen as a byproduct, a waste product of their respiratory cycle. So there's a balance between what plants take in and give off to what animals take in and give off, sort of the yin and the yang. animals absorb the waste product of plants, and plants absorb the waste product of animals gaseously. So that's a balanced relationship. So it's something to think about when you see or hear or read of the environmental challenges that we face, with climate change and the greenhouse effect and things like that. Those are disrupted or exaggerated by our behavior in destroying plant habitats. When we cut down a forest to build a shopping mall or a meatpacking plant or something, when you take away the plants that we have evolved to live with in balance because they absorb our waste product, carbon dioxide, and they expel our essential gas, oxygen, we've grown up as a species, so to speak, in that balance. But as our species is cutting down, mowing over, paving over, and otherwise destroying living plants, we are essentially slowly turning off the oxygen valve. Slowly but surely removing all of the organisms that produce the environment in which we require to live. So that's scary. All right, so 78% nitrogen, 21% oxygen, just less than 1% carbon dioxide. And then if you look down further on this components slide, or today's atmosphere slide, you'll see there are other gases, including argon, which is a inert gas, water vapor, very important gas, H2O, and other trace gases like your fluorine and helium and hydrogen and xenon. I mean, the list goes on, but they are all minuscule, tiny percentages of a percent that we don't really need to spend much time focusing on them. The big ones are the nitrogen, the oxygen, carbon dioxide, and water vapor. Those are your main, the main components that we will focus on. Okay, so these gases, as previously stated in leading up lectures to this, are a dynamic system. They're in constant motion. There's a slight breeze out today. It's absolutely beautiful here on the pool deck. Absolutely beautiful. But there's a constant motion due to temperature differentials, as discussed, cloud cover, of which there's none today. And not only is there physical motion, there's actually chemical interaction going on. There's continual cycling and recycling and breaking of bonds and forming of new bonds constantly. So we're going to look at a few of the different cycles. The cycle indicates a starting point with certain ingredients, a process through which those ingredients go, and an end result with different ingredients, and it happening over and over again, cyclically. So it's about balance and change, equilibrium, and continuation, constant circle. All right. You're familiar maybe a bit with the water cycle. You're familiar maybe a little bit with the carbon cycle. But the nitrogen cycle is where I want to start off because it's probably the newest to most of you. Okay? So I've advanced to the next slide entitled nitrogen. Okay? And nitrogen, as stated earlier, is the most abundant gas. Abundant means it is it's all around us. If you were to take a handful of air, almost all of that air in this handful is nitrogen. It's 80% nitrogen, 78 to be specific. And although we can't use nitrogen directly out of the atmosphere, people can't breathe it in and breathe it out and have any absorption of it, we do rely on nitrogen to build up our tissues. Super important. Nitrogen is one of the major essential elements for proteins. And we're made up of proteins. Chickens are made up of proteins, cows are made up of proteins, eggs are proteins. When you think about a dietary food pyramid, you need a certain amount of protein in your diet, and that's because we need to assimilate, to absorb, digest, and transform those animal or vegetable proteins into human proteins in order for you to grow, to build muscle mass, to get taller, to develop immunoresponses. All of the functions that make us what we are run and built by proteins. And the primary molecular foundation of proteins is nitrogen. So we need nitrogen, but we cannot get or access nitrogen from the atmosphere. Got my bag of ice. Got to keep cool out here. It's like 82 degrees right now. It's not even noon. All right, so as stated, we can't, neither plants nor animals can absorb this nitrogen directly out of the atmosphere. It has to be cycled in to plants and animals' systems by means of transport vehicles, if you will. And we get our nitrogen, people get our nitrogen by eating, by ingesting tissues that have, plant tissues or animal tissues that have nitrogen in them, proteins. And plants, as we know, plants don't eat, they photosynthesize and sort of produce their own food. But they do require nitrogen to build up their plant tissues. And there is another bacterium that plays a very important role in bridging the gap between atmospheric nitrogen and biotic nitrogen in an organism. Okay, atmospheric nitrogen is gaseous N2. Biotic, meaning being in a living organism, has to get there by being linked to other atoms making larger molecules of things like nitrates and nitrites and ammonia. And all of these components are created through bacterial metabolism. There's another bacterium that is very beneficial, absolutely essential for all life on Earth, called nitrogen-fixing bacteria. Nitrogen fixing. It doesn't mean that nitrogen is broken and needs to be repaired. Nitrogen fixing means you're sticking nitrogen to something else. If you've ever heard to, affix the decal in the upper right corner of your rear window. Affix, to affix a label, is to stick it. So fixing, in this scientific sense, is to stick nitrogen onto something. So nitrogen-fixing bacteria is a very common bacteria that lives in soil that does the job of absorbing gaseous nitrogen, linking it to a hydrogen, and creating, as a byproduct, a nitrite, an actual usable NH2 molecule that plants now can absorb through their roots and assimilate into their system. And then there is another bacteria on the other end of this cycle that helps decompose dead plant material and unfix the nitrogen and release it back into the environment. And that's a little bit of foreshadowing into the nitrogen cycle. So Our next lecture, this was a good introduction to the components and the cycle. Our next lecture, because we're hitting 20 minutes now, our next lecture, I guess tomorrow, will be entirely on the nitrogen cycle. What it is, what's involved in it, what is made, what goes into it, what comes out of it. Hint, it's all about nitrogen and what it is stuck to. Okay? Hope that was a reasonable time. Know a little bit more. Log back on for the next lecture. Probably tomorrow or the next day. All right? Take care. Hope all's well.